Hi, this is Dr. George Sweeney, and what we're going to do today is we're going to take a look at finding basic Laplace transforms. So in a previous video, we talked about what the Laplace transform was, and then we talked about what are those basic Laplace transforms that we can use so that we don't have to do the integration. What we're going to do now is we're actually going to give a couple of examples of how to go about transforming functions into their Laplace transforms. And we're going to utilize a couple of techniques that we have from integration. We'll talk a little bit about those at the very beginning. So here's our list of standard Laplace transforms. And we talked about these in the last video, so I'm not going to go over them again, but I am going to be utilizing them. And for each one of the examples that I have, I'll come back and reference them again. So the Laplace transform is going to be an integral, and it's going to be linear. And that is, it'll carry over all the properties of the integral. This means we can pull out scalars and separate out addition and subtraction. This does not, however, mean that we can multiply or divide. And so we're just going to look at what does it look like to pull out the scalars, okay, and what does it look like to multiply or divide. So to be more explicit, we're going to be able to do the following. So what you're going to notice here is our definition of the Laplace transform, but what we've done is we've multiplied it by a scalar, okay? And so that scalar can then be brought out because we can do that utilizing integration. And so consequently what we get is we get the scalar times the Laplace transform. And so it's a pretty simple principle, but I wanted to make sure that we see what it looks like as an integral. We can also do that for addition. And with addition, you'll see if we have the Laplace transform for the addition of two functions that we can take Laplace transforms of, what we'll get is we can separate out that addition, okay? And that means that we'll have the Laplace transform of each individual function added together, okay? We're going to utilize those principles and some trig conversions and maybe even partial fractions a little bit later on to expand the range of functions that we can find Laplace transforms for. So let's take a look at our first example where we're going to do some scalar multiplication. So we'll find the Laplace transform for f of t equals 6 sine 3t. Now we know the Laplace transform for sine of bt is going to end up equaling b over s squared plus b squared. In our example, b is going to equal 3, and we're going to have a scalar of 6. So the Laplace transform of 6 sine 3t is going to end up equaling 6 times the Laplace transform of sine 3t, and that's because of that scalar multiplication property that we saw earlier. So in this case, b being 3 means that we're going to get 6 times 3 over s squared plus 3 squared. So that means that we have 18 over s squared plus 9. And that, in fact, is the Laplace transform for 6 sine 3t. Now let's take a look at addition. So let's say, for example, we want to find the Laplace transform for g of t equals e to the negative 2t plus 4t squared. So in this case, we'll have two functions. We're going to have h of t equal to e to the negative 2t, and we'll have f of t equal to 4t squared. The Laplace transform, we'll put these on the side, the Laplace transform for e to the at is going to equal 1 over s minus a. And the Laplace transform for t to the n is going to equal n factorial divided by s to the n plus 1. So the Laplace transform for e to the negative 2t plus 4t squared is going to end up equaling the Laplace transform for e to the negative 2t plus the Laplace transform for 4t squared. That's going to end up equaling then, well, the first one, we've got 1 over s minus a. A is going to equal negative 2, so this is going to be 1 over s plus 2 plus, and then we'll pull out the scalar 4, so this is going to be 4 times, and t squared, so we have 2 factorial divided by s to the 2 plus 1. When we simplify, we're going to end up with 1 over s plus 2 plus 8 over s cubed. And that is the Laplace transform for g of t. So you can see, all we've got to do is we've just got to separate out the two functions, and we have Laplace transforms for each individual one. Go ahead, find the Laplace transforms and add them together. In our third and final example, we're going to take a look at utilizing a trig substitution. Now, there are a lot of different kinds of trig substitutions that you might use. Or we might actually use different kinds of algebraic substitutions depending upon the kind of Laplace transform that we're looking at. To go through all of them would be kind of difficult because there really are a really wide range. But let's take a look at f of t equals 4 sine of t minus pi over 4. Now, I don't actually have a Laplace transform or a simple to use integral that I can, or property of integrals like addition or scalar multiplication that I can use in order to transform this. But I do actually have a trig substitution. I know that the sine of pi minus, or excuse me, t minus pi over 4 is going to end up equaling sine of t cosine negative pi over 4 plus the sine of negative pi over 4 cosine of t, utilizing my addition of sine, the addition of angles formula for sine functions. You can also use, by the way, a subtraction one. I just happen to utilize it using a negative pi over 4. So now this is going to end up equaling sine t, and cosine negative pi over 4 is going to be times root 2 over 2, plus, and this will be then negative root 2 over 2 cosine t. Now I'm going to substitute back in, so f of t is now going to equal 4 times root 2 over 2 sine t minus square root of 2 over 2 cosine t. And so that's going to end up equaling, if we go in and we multiply through by 4, we get root 2 sine t minus root 2 cosine t. Well, now I can actually go find the Laplace transform of that. So doing the trig substitution beforehand allows me to now do the Laplace transform. So the Laplace transform of root 2 sine t minus square root of 2 cosine t is going to equal the square root of 2 times the Laplace transform of sine t minus the square root of 2 times the Laplace transform of cosine t. Now, all we've got to do there is use the addition and our scalar multiplication in order to actually go through and make that transformation. So now this is going to then equal the square root of 2 times, and this will be 1 over s squared plus 1 squared, minus, and then this will be the square root of 2 times s over s squared plus 1 squared. And that's because the Laplace transform of cosine bt is equal to s over s squared plus b squared. Finishing up my simplification, I get root 2 over s squared plus 1 squared minus the square root of 2, or s root 2 over s squared plus 1 squared. And I can actually rewrite that as square root of 2 times 1 minus s over s squared plus 1. And that is my Laplace transform. So just a little bit of trig substitution and then some algebra will allow you to kind of expand out the number of Laplace transforms that you can use. So what we've done here inside of this video is we've taken a look at how do we use scalar multiplication and addition, as well as some facts that we know about trigonometry or about algebra, if you see some exotic kind of Laplace transforms, in order to expand your repertoire of the Laplace transform and be able to do more with them. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.